This phone has close to 10 billion transistors in it, each being 3 to 5 nanometers in size, about the size of a few strands of DNA. Transistors are basically switches turning on and off billions of times per second. Combined in circuits, they perform complex calculations in fractions of seconds. Guys, stay tuned, as today we will dissect and explore one of the most important and fundamental inventions in human history, the transistor. It's 1945 and the first programmable digital computer is born. It's called the ENIAC. It was revolutionary at the time, consisting of 18,000 vacuum tubes. You see, vacuum tubes were key to turning on and off the flow of current in the first generation of computers, which enabled them to perform complex calculations and tasks. A vacuum tube is basically a switch consisting of an anode, cathode, and a heater, all of which are concealed in a glass vacuum chamber. When the heater is powered, the heat in the tube causes electrons to flow from the anode to the cathode. But there were a lot of problems with these tubes. They broke down constantly, emitted a lot of heat, and with the large number of tubes needed, the computer consumed a lot of power. Then, in 1947, the first solid-state transistor was invented, made from germanium. This revolutionary device was much smaller, consumed far less power, and enabled faster switching operations than the vacuum tubes. Scientists realized the potential of the transistor, which led to the computing revolution. Today we'll be talking about MOSFETs. There are many types of transistors, mainly BJTs and MOSFETs. Now, because I want to have a life while making these videos, I'll be covering BJTs in another video, so subscribe so you won't have to miss it. So a MOSFET, or metal oxide semiconductor field effect transistor, don't get overwhelmed by the name, it's pretty simple once you understand how it works. So a MOSFET is basically a switch consisting of a source and a drain, which are the entry and exit points of the current through the transistor. The third element of the transistor is the gate. Now, the gate is what allows or restricts the current to flow through the channel from the source to the drain. So when the gate is closed or off, current can't flow, and when on, current will flow between the source and the drain. Pretty simple, right? We can actually represent this in binary form. When the transistor is on, this is 1, and when off, this is 0. The gate does this by changing its charge state. For example, in this case, as the gate has a negative charge, it will attract positive charges to the channel. But now, the gate has a positive charge. This attracts negative charges to the channel, which allows the flow of electrons from the source to the drain, resulting in a flow of current through the transistor. The example I just showed you is a negative channel transistor, or NMOS. This type of transistor has a current flow when the channel is negatively charged, hence the charge carriers are electrons. The opposite of this device is a PMOS device. Current flows through this transistor with a positive charge in the channel, meaning that the carriers are holes. Joined together, these two devices form CMOS, which are extensively used in modern electronics, such as chips and CPUs. Let's understand how these transistors perform complex computations. As an example, let's say we have two transistors arranged in this configuration. If either A or B, or both of them, are off, there will be no current flow. Only if both are on will there be a flow of current. Let's take another example. In this configuration, when A or B are on, current will flow, and if both are on, current will still flow. To stop the flow of current, they have to be both in the off position. You see where I'm going with this, right? If you have or had engineering or computing at school, you may have covered logic gates such as AND, OR, and NOT. Transistors are the basis of these logic gates. We've taken quite simple configurations, but in more complex circuits, such as this, we can perform complex computations. You may come across the terms depletion and enhancement type MOSFETs. These are basically modes of how a MOSFET could operate. Enhancement mode, the most common of the two, is when no current can flow between the source and the drain unless a voltage is applied at the gate. When a gate voltage is applied, this enhances the channel and current can flow. What is illustrated is an NMOS device. However, the analogy is the same in a PMOS. In depletion mode, the MOSFET has a conductive channel in the off position. So when there is no voltage applied at the gate, the channel is already conductive and the current is flowing between the source and the drain. To restrict or stop the flow of current, a gate voltage is applied, which depletes the channel. An easy way to remember the difference is to associate the enhancement mode with a normally open switch and the depletion mode with a normally closed switch. MOSFETs are a type of field effect transistor. Now, to understand why it's called this, take a look at this diagram. As you can see, between the gate and the substrate, there is a thin oxide layer. This layer acts as a barrier insulating the gate from the source and the drain. When a voltage is applied at the gate, this creates an electric field across the oxide layer. This electric field attracts or repels the corresponding charges in the gate, controlling the flow of current between the source and the drain. From the humble beginnings of the ENIAC, which took up 28 square meters of space, to phones that fit in our pockets, all this scaling down in a span of less than 100 years. So the next time you're using your phone or while watching this video, remember that there are billions of transistors at work behind that screen. I hope you enjoyed this video. If you did, don't forget to subscribe and let me know what you think in the comments below. Also, thank you very much for watching and watch this video next.